Hello, and welcome. Before we begin our quiet journey through the universe, take a gentle moment to subscribe to the channel if you enjoy calm science stories like this. It helps this space grow and allows more curious minds to drift into these peaceful explorations of the cosmos. Now, settle in, relax, and let your mind slowly travel outward. Tonight, we explore one of the most fascinating questions in astronomy. Somewhere in the deep darkness of our galaxy exist stars so enormous that, if one replaced our sun, its outer layers could stretch past the orbit of Jupiter, sometimes even farther. Astronomers sometimes describe these giants with dramatic words: cosmic titans, stellar giants, even behemoths. But the real scientific question is quieter and much more precise. Is there truly a star so large that it deserves that title? Or do these claims come from misunderstandings about how astronomers actually measure stars across immense cosmic distances? To understand the answer, you first need to look closely at something surprisingly subtle. Because in astronomy, the word largest does not always mean what you might expect. When you hear that a star is the largest ever discovered, your mind may picture something immense, stretching far beyond imagination. Yet in astronomy, the word largest has a very precise meaning. It does not simply refer to something that looks bright or appears impressive in a photograph. It depends on measurable physical properties, each defined carefully and tested against observation. You begin with radius. The radius of a star is the distance from its center to its surface. If you imagine drawing a straight line from the very core outward until you reach the outer layer where light escapes into space, that length is the star's radius. When astronomers speak of the largest stars by size, they often mean the ones with the greatest radius. Some stars expand so much that, if placed where the sun sits in our solar system, their outer layers would extend beyond the orbit of Mars or even Jupiter. But radius is only one way to measure greatness. Mass is different. Mass tells you how much matter a star contains. It determines how strong its gravity is and how much pressure builds in its core. A star with more mass squeezes its central hydrogen more tightly, causing nuclear fusion to proceed at a faster rate. This changes the star's temperature, brightness, and lifespan. The most massive stars are not always the ones with the largest radii. Some extremely massive stars remain comparatively compact, while others with lower mass swell outward late in their lives. Then there is luminosity. Luminosity measures how much energy a star releases per second. It is the true brightness of the star, independent of how far away it is. A star may appear faint from Earth simply because it lies at a great distance. Luminosity corrects for that distance and tells you the actual power output. Some stars shine hundreds of thousands of times more brightly than the sun, even if their physical size is not the largest known. These three quantities, radius, mass, and luminosity, are related, but they are not interchangeable. A large radius does not automatically mean high mass. High luminosity does not guarantee the greatest physical diameter. When astronomers compare stars, they must first decide which property they are discussing. Without that clarity, the word largest becomes misleading. You may wonder how these measurements are even possible. After all, stars are so distant that they appear as tiny points of light, even through powerful telescopes. Unlike planets in our own solar system, their surfaces cannot usually be resolved in detail. Yet careful observation and physics allow you to determine their properties with surprising accuracy. Distance is one of the most important pieces of information. To measure true luminosity, astronomers must know how far away a star is. For nearby stars, parallax provides this measurement. As Earth orbits the sun, a nearby star appears to shift slightly against the background of more distant stars. By measuring that tiny shift and applying geometry, astronomers calculate distance. The European Space Agency's Gaia mission has refined these measurements for more than 1 billion stars, improving accuracy across our region of the galaxy. Once distance is known, apparent brightness can be converted into luminosity. If a star looks bright and is very far away, it must be extraordinarily luminous. If it appears bright but is nearby, its true power may be more modest. Surface temperature is determined using spectroscopy. When starlight is spread into a spectrum, dark absorption lines appear at specific wavelengths. These lines correspond to elements in the star's atmosphere. The pattern of lines, along with the overall color of the spectrum, reveals temperature. A hotter star emits more blue light, while a cooler star emits more red light. Temperature, combined with luminosity, allows astronomers to calculate radius through the Stefan-Boltzmann law. This physical law relates a star's energy output to its surface area and temperature. If you know how much energy is emitted and how hot the surface is, you can solve for the total surface area, and from that derive the radius. This method shows why definitions matter. A star might be extremely luminous because it is very hot, not because it is physically large. Another might be cooler but enormous in radius, spreading moderate heat over a vast surface. Both can appear extraordinary, yet in different ways. There are also rare cases where astronomers can measure a star's angular diameter directly. Using interferometry, multiple telescopes work together to simulate a much larger instrument. For a small number of nearby giant stars, this technique reveals a measurable disk rather than a point of light. From angular size and distance, the physical radius can be calculated more directly. Even then, uncertainties remain, especially if the star has an extended atmosphere that gradually thins into space rather than ending sharply. You begin to see that calling a star the largest ever discovered requires careful qualification. Are you speaking of radius? Of mass? Of luminosity? Are the measurements precise? Or do they carry wide margins of uncertainty? Science progresses by refining these values over time, sometimes adjusting rankings as better data arrives. This careful approach does not diminish the wonder. Instead, it deepens it. The fact that you can measure the size of a star thousands of light years away using geometry, spectroscopy, and physical laws tested in laboratories on Earth is a quiet triumph of human understanding. As you rest with these distinctions, radius, mass, luminosity, you prepare your mind to explore how astronomers push these measurement techniques across far greater distances, where even the faintest points of light can reveal astonishing scale through the steady application of physics and observation. When you look at a star in the night sky, it appears as a small, steady point of light. Even through a powerful telescope, most stars remain unresolved, too distant for their surfaces to appear as disks. Yet from that tiny point you can measure something vast. You can determine its size. The process begins with distance. Without knowing how far away a star is, you cannot know its true brightness, and without true brightness you cannot calculate its radius. For stars relatively close to Earth, astronomers use parallax. As Earth moves around the Sun during the year, nearby stars appear to shift slightly against the background of more distant stars. This shift is extremely small, often less than a fraction of an arcsecond, but it can be measured precisely with modern instruments. Using simple geometry, that shift gives you the star's distance. Once distance is known, apparent brightness becomes meaningful. A star that appears faint but lies very far away may actually be releasing enormous amounts of energy. Brightness as seen from Earth decreases with the square of the distance. If you double the distance, the brightness becomes 4 times weaker. By reversing this relationship, astronomers calculate luminosity, which is the total energy emitted per second. Now you have 2 key pieces of information: luminosity and surface temperature. Surface temperature is measured using spectroscopy. When starlight is spread into a spectrum, it reveals a pattern of absorption lines caused by elements in the star's outer layers. The distribution of light across different wavelengths also shows the star's temperature. Hotter stars emit more of their energy in shorter wavelengths, toward the blue and ultraviolet. Cooler stars emit more in longer, red wavelengths. With luminosity and temperature together, you apply the Stefan-Boltzmann law. This law states that the total energy radiated by a surface depends on its temperature and surface area. More specifically, luminosity equals the surface area multiplied by a constant and by the temperature raised to the 4th power. Because temperature has such a strong influence, even small differences matter. If 2 stars have the same luminosity but different temperatures, the cooler one must have a larger surface area to emit the same total energy. From surface area, you calculate radius. This method allows astronomers to estimate the size of stars thousands of light years away without ever seeing their surfaces directly. The calculation rests on physical laws tested in laboratories and confirmed through repeated observation. For some stars, especially large and nearby giants, there is another approach. Interferometry combines light from multiple telescopes separated by some distance. By analyzing how light waves interfere with each other, astronomers can measure extremely small angular sizes. Instead of appearing as a perfect point, a few stars reveal a measurable disk. When you combine angular diameter with distance, you obtain the physical radius more directly. However, most stars are too distant for this method. For them, the indirect method using luminosity and temperature remains essential. The accuracy of the result depends heavily on distance measurement. Even a small error in distance can significantly change the calculated luminosity, and therefore the derived radius. For stars beyond the reliable range of parallax, astronomers turn to standard candles. These are objects whose intrinsic brightness is known through well-understood physical processes. Certain types of variable stars, such as Cepheid variables, change brightness in a predictable way that relates directly to their true luminosity. By observing the pattern of variation, astronomers determine luminosity and then calculate distance. This extends measurement far beyond nearby stars. Still, uncertainties remain. Interstellar dust can dim and redden starlight. If dust absorption is not properly accounted for, a star may appear less luminous than it truly is. Astronomers correct for this effect by studying how light at different wavelengths is absorbed, but the correction is not always perfect. Another challenge arises with very large stars that possess extended atmospheres. Red supergiants, for example, do not have sharply defined surfaces like solid objects. Their outer layers gradually thin into space. When defining radius, astronomers must choose a specific layer where the star becomes optically thin, meaning light can escape freely. Different methods may yield slightly different boundaries. Variable stars add further complexity. Some giant stars expand and contract over time, causing changes in luminosity and temperature. If measurements are taken at different phases, derived sizes may differ. Careful monitoring over long periods helps reduce this uncertainty. Despite these challenges, the overall framework remains stable. Distance gives luminosity. Spectroscopy gives temperature. Physics connects luminosity and temperature to surface area, and surface area leads to radius. Each step builds upon well-tested principles. Each measurement includes uncertainties, but those uncertainties are quantified and openly reported. You begin to appreciate how much information is contained in a simple point of light. The brightness reaching your eyes carries evidence of temperature, size, and distance. With careful instruments and steady analysis, that light becomes data, and that data becomes knowledge. As you rest with this understanding, you sense how remarkable it is that geometry and thermodynamics allow you to measure objects so far away. And as stars grow larger and more distant, these same methods are pushed carefully to their limits, revealing just how far precision can reach across the galaxy. You begin in a cold, dark region of space where dense clouds of gas and dust drift quietly within a galaxy. These molecular clouds are mostly hydrogen, with traces of helium and heavier elements formed in earlier generations of stars. Though they appear calm, gravity is always at work. Over time, small variations in density allow certain regions to gather more material than their surroundings. As mass accumulates, gravity strengthens, and collapse begins. As the cloud contracts, gravitational energy converts into heat. The central region grows denser and hotter. When enough mass gathers, the temperature in the core rises to millions of degrees. At this point, hydrogen nuclei begin to fuse into helium. Nuclear fusion releases energy in the form of light and radiation. This outward pressure balances the inward pull of gravity. A stable star is born. If the forming star gathers a large amount of mass, its future will be very different from that of a smaller star like the Sun. Mass determines core pressure. Greater mass means stronger gravity, which compresses the core more intensely. This compression raises the core temperature higher than in lower mass stars. Because nuclear fusion rates depend strongly on temperature, fusion proceeds much faster in massive stars. You might expect that a star with more fuel would live longer. In reality, the opposite occurs. Although massive stars contain far more hydrogen, they burn through it at a much greater rate. The relationship between mass and luminosity shows this clearly. Luminosity increases steeply with mass. A star 10 times the sun's mass may shine thousands of times more brightly. That enormous energy output reflects a rapid consumption of fuel. During the stable phase of hydrogen fusion, called the main sequence, the star maintains balance between gravity and outward radiation pressure. Yet for massive stars, this phase is brief in astronomical terms. Instead of lasting billions of years like the Sun, it may last only a few million years. The higher the mass, the shorter the stable period becomes. When hydrogen in the core becomes depleted, the balance changes. Fusion slows in the center, and gravity causes the core to contract. As it contracts, temperature rises further. This increased temperature allows new fusion processes to begin, first in a shell around the core, and then in the core itself as helium begins to fuse into heavier elements such as carbon and oxygen. While the core contracts and heats, the outer layers respond differently. Energy produced in shell fusion pushes outward, and the star's outer envelope expands dramatically. The surface cools as it spreads over a much larger area. The star becomes a supergiant. Its radius can grow hundreds or even more than 1,000 times larger than the Sun's. This expansion does not mean the star has gained mass. In fact, massive stars often lose mass through powerful stellar winds. Radiation pressure drives material away from the surface at high speeds. Over time, significant amounts of matter can be carried into surrounding space. Even so, the remaining outer layers expand greatly due to internal changes in energy production. Inside the core, fusion continues through successive stages. After helium, heavier elements fuse in sequence: carbon, neon, oxygen, and silicon. Each stage occurs at higher temperatures and for shorter durations. Fusion of silicon into iron lasts only a short time compared to earlier stages. Iron marks a turning point because fusing iron does not release energy. Instead, it consumes energy. Once the core becomes primarily iron, no further energy-producing fusion can occur. Without outward pressure from fusion, gravity takes control. The core collapses rapidly, leading to a supernova explosion for the most massive stars. In that final event, elements heavier than iron are formed and scattered into space. What remains may become a neutron star or a black hole, depending on the original mass. Before this final collapse, however, the star may reach extraordinary size. In the red supergiant phase, the outer envelope can extend so far that, if placed in our solar system, it would stretch beyond the orbit of Earth and sometimes much farther. Despite this enormous radius, the surface temperature is relatively cool compared to hotter blue stars. The reddish color reflects this lower surface temperature, even though the core remains extremely hot. You begin to understand how size emerges from internal physics. High mass leads to high core temperature. High temperature drives rapid fusion. Rapid fusion changes internal structure quickly. These changes cause outer layers to expand, producing vast radii. The largest stars by size are often those nearing the end of their lives, temporarily swollen by the complex balance between gravity and fusion. Throughout this process, physical laws remain consistent. Gravity pulls inward according to mass. Radiation and gas pressure push outward according to energy production. The interplay between these forces shapes every stage of a massive star's life. As you rest with this steady progression from cloud collapse to fusion, from main sequence to supergiant, you see how the greatest stellar sizes are not permanent conditions but phases within a larger evolution shaped by temperature, pressure, and time. When a massive star exhausts hydrogen in its core and begins fusing heavier elements, its structure changes in a profound but orderly way. The core contracts under gravity and grows hotter, while energy produced in surrounding shells pushes outward. This outward pressure causes the outer layers to expand dramatically. The star enters the phase known as a red supergiant. You notice first the scale. A red supergiant can reach hundreds or even more than 1,000 times the radius of the Sun. If such a star were placed at the center of our solar system, its outer layers could extend beyond the orbit of Mars, and in extreme cases approach the orbit of Jupiter. Yet this enormous size does not mean the star is equally dense. In fact, the average density of a red supergiant is extremely low. Its vast envelope is spread over an immense volume. The reason for this expansion lies in the balance between gravity and energy production. As fusion proceeds in shells around the contracting core, energy flows outward through radiation and convection. Convection becomes especially important in these stars. Large regions of hot gas rise toward the surface, cool slightly, and sink again. These convective cells can be enormous, covering a significant fraction of the star's visible surface. Surface gravity in a red supergiant is relatively weak compared to smaller, denser stars. Gravity depends on mass and radius. Although these stars are massive, their radii are so large that the gravitational pull at the surface is gentle. With weaker surface gravity, gas in the outer layers is less tightly bound. This allows the atmosphere to extend far outward, forming a diffuse envelope rather than a sharply defined boundary. Because the surface layers expand so widely, they cool. Temperature depends partly on how concentrated the energy is at the surface. When the same internal energy is spread over a much larger area, the surface temperature decreases. Red supergiants typically have surface temperatures between about 3,000 and 4,500 kelvins, cooler than the Sun's surface temperature of roughly 5,800 kelvins. The cooler temperature gives them a reddish appearance when their light is analyzed. Despite their cool surfaces, their cores remain extremely hot. Deep inside, fusion continues at temperatures of millions or even billions of degrees, depending on the stage of evolution. The cool color you observe reflects only the outermost layers, not the intense activity within. Some stars evolve even further into what astronomers call hypergiants. Hypergiants are among the most luminous and massive stars known, and they often show signs of instability. Their spectra reveal strong stellar winds and significant mass loss. Material flows away from the star at high speeds, creating surrounding clouds of gas and dust. These outflows can affect how the star's size is measured, because the outer atmosphere may blend gradually into surrounding material. In hypergiants, radiation pressure becomes especially important. The intense luminosity exerts an outward force on the outer layers. When radiation pressure approaches the strength of gravity at the surface, the star can become unstable. This balance is described by the concept known as the Eddington limit. If luminosity becomes too high for the given mass, outer layers may be driven away more easily. As a result, hypergiants often experience episodes of enhanced mass loss. Observationally, measuring the size of red supergiants and hypergiants presents challenges. Their extended atmospheres do not have a solid surface. Instead, the density of gas decreases gradually with distance from the core. Astronomers must define a specific layer where the star becomes optically thin, meaning light can escape freely without further scattering. Different observational techniques may probe slightly different depths, leading to variations in reported radii. Variability adds another layer of complexity. Many red supergiants are semi-regular variables. Their brightness changes over time due to pulsations and convection. As the star expands and contracts slightly, temperature and luminosity shift. These changes can alter calculated radius values if measurements are taken at different times. Careful monitoring over long periods helps astronomers average these variations and obtain more stable estimates. Infrared observations are often crucial. Because red supergiants emit much of their energy at longer wavelengths, infrared telescopes provide clearer data. Infrared light also penetrates interstellar dust more effectively than visible light. This is especially important because many of the largest stars are located in regions of the galaxy rich in gas and dust, which can obscure optical measurements. You begin to appreciate that the term largest becomes particularly sensitive in this context. A small adjustment in estimated distance can significantly change luminosity. A slight revision in temperature measurement can alter the calculated radius through the Stefan-Boltzmann relationship. Extended atmospheres and mass loss blur the outer boundary. Each factor contributes to uncertainty. Yet even with these challenges, the overall picture remains consistent. Red supergiants and hypergiants represent late evolutionary stages of massive stars. Their enormous radii arise from well-understood physical processes: core contraction, shell fusion, convection, and weakened surface gravity. Their cool temperatures reflect expanded outer layers rather than diminished energy production. Their instability signals the final phases of stellar evolution. As you consider these immense, diffuse stars, you sense how their size is not a permanent attribute but a stage shaped by internal physics. Among them are specific objects whose estimated radii stretch the limits of measurement, inviting careful comparison and steady evaluation through observation and calculation. Uy Scuti is a star that quietly commands attention in the constellation Scutum. When astronomers study it, they do not rely on photographs or direct observation of a surface. Instead, they examine the light it emits, analyze its spectrum, and calculate fundamental properties using well-established physics. Its size, enormous by any standard, has made it a focal point for studies of extreme stellar radii. The first step in estimating Uy Scuti's radius is determining its luminosity. Luminosity depends on how much energy the star releases per second. Observers measure the apparent brightness from Earth, then combine that information with distance to calculate total power output. Apparent brightness alone is not enough. The star could appear dim simply because it is far away, while a nearby star may appear bright even if its true luminosity is lower. Correcting for distance is therefore essential. Distance estimation introduces uncertainty. Uy Scuti lies thousands of light-years from Earth, far enough that parallax measurements are challenging. For nearby stars, parallax provides highly accurate distances, but at Uy Scuti's range, the shift is extremely small, approaching the limits of detection even for precise instruments. Astronomers must supplement parallax with other methods, including comparisons to similar stars in its region and models of galactic structure. Each method carries a margin of error that propagates through to the final radius estimate. Once luminosity is established, temperature measurements follow. Spectroscopy reveals the star's surface temperature by examining absorption lines and the overall distribution of emitted light across wavelengths. Uy Scuti, like other red supergiants, has a relatively cool surface compared to hotter, smaller stars. Its effective temperature, combined with luminosity, allows application of the Stefan-Boltzmann law to estimate surface area, and therefore radius. This method is the standard approach for distant stars with unresolved disks. Results indicate an extraordinarily large radius. Estimates suggest that Uy Scuti's outer layers could extend over 1,000 times the radius of the Sun. If placed at the center of our solar system, the star would reach beyond the orbit of Jupiter, encompassing the inner planets. The sheer scale challenges the mind, yet the calculation rests on measurable, verifiable physics. Still, astronomers proceed with caution. Distance errors, temperature uncertainties, and variability in the star itself mean that the radius cannot be pinned to a single exact number. Uy Scuti, like other red supergiants, pulsates slightly. Convection within its outer layers and mass loss through stellar winds create fluctuations that affect measured luminosity and inferred size. By averaging multiple observations over time, astronomers reduce the influence of these variations. Advanced instruments, including space-based telescopes and interferometric arrays, provide additional data points. Observing in different wavelengths, particularly infrared, helps penetrate dust that can obscure measurements. Dust in the interstellar medium absorbs and scatters visible light, potentially making the star appear dimmer than it truly is. Correcting for this effect is essential for accurate radius estimates. Another challenge arises from the star's extended atmosphere. Unlike a solid object, Uy Scuti does not have a sharply defined surface. The outer layers gradually thin into space. Astronomers must decide at which optical depth to define the radius. Different conventions can yield slightly different results. Some studies report a radius corresponding to where the optical depth reaches a standard value, while others use slightly deeper or shallower layers. Each approach is scientifically justified but leads to variation in reported values. The star's mass also plays a role indirectly. While Uy Scuti's mass is high, it is not the largest known by mass. Its extreme radius arises from evolutionary stage and internal structure rather than sheer mass alone. Red supergiants expand outward as they evolve, driven by shell fusion and core contraction. The interplay between gravity, radiation pressure, and convective processes sets the outer envelope's extent. Observational history shows how estimates evolve. Early studies suggested even larger radii, but improved distance measurements and better understanding of interstellar absorption refine the values. Scientific revision is a natural part of the process. Each refinement improves confidence, yet absolute certainty remains elusive when studying objects so far away. Comparing UY Scuti with other enormous stars, astronomers emphasize consistent methodology. Differences in measurement techniques or assumptions can lead to apparent contradictions. When multiple research groups apply similar methods, results converge, providing more reliable rankings. This illustrates the broader principle that science advances through careful observation, repeated measurement, and transparent reporting of uncertainties. You notice that UY Scuti exemplifies both the power and limitations of stellar measurement. On one hand, you can calculate a radius far beyond ordinary human scales using light, physics, and distance. On the other hand, you recognize that exact rankings may change as methods improve. Largest becomes a provisional title, dependent on the precision of observation and interpretation. Despite these caveats, UY Scuti remains a symbol of extreme stellar evolution. Its expanded envelope represents the natural consequence of high mass, core contraction, shell fusion, and low surface gravity. Its cool surface reflects the energy spread over an immense area. Its variability and mass loss remind you that stars are dynamic objects, not static spheres. As you consider this star in the quiet of space, you sense how measurement, physics, and careful observation combine to reveal scale that is almost incomprehensible. And in thinking about UY Scuti, you prepare to examine other extreme stars, each offering its own insights into the upper limits of size and the evolving methods astronomers use to determine them. Stephenson 2-18 is a star that resides within a dense cluster in the constellation Scutum, known as the Stephenson 2 Association. Like UY Scuti, it captures attention because of its extraordinary estimated radius. Observers cannot directly resolve its surface, but they can measure the light it emits and interpret that information through established physical laws. Its scale is staggering, and yet the process of determining that scale requires careful attention to detail. The first step in estimating Stephenson 2-18 size involves measuring distance. Unlike isolated stars, this one is part of a cluster. Astronomers analyze the cluster's collective properties, comparing its stars to standard stellar models. By examining the color and brightness of several members, they can infer the distance to the entire group. Small differences in these calculations can significantly affect the derived radius for Stephenson 2-18 because luminosity scales with the square of distance. Once distance is estimated, astronomers measure apparent brightness. Light reaching Earth is affected by interstellar dust, which absorbs and scatters photons. Because the cluster lies within a region rich in gas and dust, correcting for absorption is crucial. Observations in the infrared help bypass much of the obscuration, revealing a clearer picture of the star's true luminosity. This step is essential for determining the energy output and, indirectly, the size of the star. Spectroscopic analysis provides the surface temperature. By spreading the star's light into a spectrum, astronomers identify absorption lines corresponding to various elements in the atmosphere. These lines, together with the overall color distribution, allow precise estimation of the effective temperature of the star's outer layers. Stephenson 2-18, like other red supergiants, has a relatively cool surface compared to smaller, hotter stars. This temperature, combined with luminosity, feeds into the Stefan-Boltzmann relation to derive the radius. The derived radius is immense. Estimates suggest it could exceed 1,000 times the Sun's radius, placing it among the largest stars known. If it were at the center of the solar system, its outer layers would extend beyond the orbit of Jupiter, swallowing the inner planets. Despite this enormous scale, the measurement comes with uncertainties, particularly due to distance and the extended, diffuse nature of its atmosphere. Like other red supergiants, Stephenson 2-18 exhibits variability. Its outer layers pulsate slowly, and convection within the envelope can create fluctuations in brightness. These variations influence temperature estimates and, consequently, radius calculations. By observing the star over extended periods and averaging data, astronomers can reduce the impact of these pulsations, but they cannot eliminate all uncertainty. The extended atmosphere presents another challenge. Red supergiants do not have sharp, well-defined surfaces. The outer envelope gradually becomes less dense until it blends with surrounding space. Astronomers must define a boundary based on optical depth, where the atmosphere becomes effectively transparent to light. Different choices in this definition can yield slightly different radius values, which is why comparing results across studies requires careful attention to methodology. Stephenson 2.18's membership in a cluster adds both advantage and complication. The cluster provides context for distance estimation, but overlapping stars and interstellar material can complicate photometric and spectroscopic measurements. Astronomers often cross-reference multiple datasets to improve accuracy, combining infrared observations, parallax where possible, and cluster models. The synthesis of these data points reduces but does not entirely remove uncertainty. In terms of luminosity, Stephenson 2.18 ranks among the brightest red supergiants known. Its high luminosity results from both its large radius and internal fusion processes. The star is in a late stage of evolution, with hydrogen already depleted in the core and heavier elements fusing in surrounding shells. Core contraction drives energy outward, inflating the outer layers and producing the enormous observed size. Despite its scale, the star's mass is moderate for a red supergiant. It is not the most massive star known, emphasizing the distinction between radius and mass. Size in these stars arises primarily from evolutionary stage and the balance of forces in their envelopes rather than sheer mass alone. This principle highlights why different stars can hold different records, depending on whether you measure radius, luminosity, or mass. Historical studies of Stephenson 2.18 illustrate the evolving nature of stellar measurement. Earlier observations suggested slightly different radii, which were later revised as instruments improved and models became more sophisticated. This process reflects the broader scientific approach. Results are provisional, subject to refinement as new data and methods become available. Even the most extreme stars can have their estimated properties adjusted over time. You begin to see that Stephenson 2.18, like other enormous stars, embodies both the power and the limits of observational astronomy. Its scale is awe-inspiring, yet its measurement relies on careful analysis, repeated observation, and correction for numerous uncertainties. Understanding its size requires attention to distance, luminosity, temperature, variability, and atmospheric structure. As you contemplate Stephenson 2.18, it becomes clear that these enormous stars are not static objects. Their radii fluctuate, their luminosity varies, and their atmospheres slowly lose mass through winds. They exist at the edge of what can be measured with current instruments, reminding you that the universe continues to challenge and refine our understanding of scale and the physical processes that govern stellar evolution. VY Canis Majoris is a red hypergiant located in the constellation Canis Major, a star whose extreme size has long fascinated astronomers. Its light reaches us across thousands of light years, carrying information about temperature, brightness, and the structure of its vast outer layers. Observing this star requires careful application of physical laws, precision instruments, and repeated measurements to understand its true nature. Early studies of VY Canis Majoris suggested that it might be the largest star known, with radius estimates placing it far beyond even UY Scuti and Stephenson 2.18. These initial calculations relied on luminosity, surface temperature estimates, and assumed distances. However, as with all distant stars, small uncertainties in these parameters produce large variations in derived radius. Initial assumptions about distance, dust absorption, and spectral characteristics led to estimates that would later be refined. Distance is fundamental. The star lies over 3,000 light-years from Earth. Parallax measurements at such ranges are difficult and often beyond direct detection. Astronomers estimate distance through indirect methods, including association with nearby clusters, modeling of stellar motions, and analysis of surrounding interstellar material. Small revisions in distance alter the calculated luminosity and, therefore, the inferred radius. In Vy Canis Majoris, even a few % difference in distance translates to hundreds of solar radii in estimated size. Luminosity itself is measured through apparent brightness, corrected for interstellar extinction. Dust and gas absorb and scatter light, particularly at shorter wavelengths, making the star appear dimmer from Earth. Observations in infrared wavelengths penetrate much of this material, providing more accurate estimates of the star's total energy output. These measurements reveal that while Vy Canis Majoris is extraordinarily bright, the precise luminosity depends on careful calibration. The surface temperature of Vy Canis Majoris is relatively cool for a hypergiant, around 3,500 kelvins. Spectroscopic analysis identifies absorption lines corresponding to elements in its atmosphere, allowing precise temperature estimates. Temperature, combined with luminosity, enables calculation of surface area using the Stefan-Boltzmann law. Early overestimates of temperature led to inflated size calculations. Improved spectral data and refined models reduced the estimated radius, illustrating the iterative nature of scientific measurement. The star's extended atmosphere adds another layer of complexity. Vy Canis Majoris does not have a sharply defined surface. Its outer layers gradually thin into space, and dense stellar winds carry material away at high velocities. These winds create shells and clumps of gas that emit light themselves, potentially confusing direct measurement of the star's photosphere. Astronomers must choose a reference layer where light escapes freely to define radius. Different choices in optical depth produce slightly different results. Variability also influences measurement. Vy Canis Majoris exhibits irregular brightness changes over months or years, driven by pulsations in its outer envelope and convective motions. These variations can affect observed luminosity and surface temperature. By monitoring the star over time and averaging multiple observations, astronomers obtain more stable estimates of its size and structure. Historical revisions highlight the self-correcting nature of astrophysics. Early estimates suggested a radius exceeding 2,000 times that of the Sun, but subsequent measurements incorporating improved distance estimates, dust corrections, and spectral analysis reduced the figure significantly. This does not diminish the star's enormity. Even revised values place it among the largest stars known, but it demonstrates the importance of careful methodology and multiple lines of evidence. Despite these adjustments, Vy Canis Majoris illustrates the physical processes that produce extreme size. Its core contraction, shell fusion, and low surface gravity drive expansion of the outer layers. Radiation pressure and convection shape the extended atmosphere, while stellar winds remove material, continually reshaping the envelope. The observed radius is therefore a snapshot of a dynamic and evolving star. You also notice the distinction between radius and mass. While Vy Canis Majoris is immense in radius, its mass is not the highest among massive stars. Its extreme size arises from its evolutionary stage and the properties of its outer envelope, not simply from the total mass of matter it contains. This reinforces the principle that radius, luminosity, and mass are related but distinct properties, each describing a different aspect of stellar physics. By studying Vy Canis Majoris, you witness the iterative process of astronomy. Initial observations generate estimates, subsequent measurements refine them, and models improve as data accumulates. Scientific understanding advances gradually, with each adjustment bringing estimates closer to reality, even for the largest and most distant stars. As you rest with the image of this hypergiant in your mind, you sense the careful balance of forces within its enormous envelope and the precision required to measure it. The story of Vy Canis Majoris reminds you that even the most extreme stars are governed by well-understood physical laws, and that scientific observation, when applied patiently, brings clarity to the vast scales of the universe. When you consider stars, it can be tempting to equate size with mass. A larger star might seem heavier, yet in astrophysics, the two are distinct properties. Radius describes how far a star's outer layers extend, while mass measures the total amount of matter contained within. A star can be enormous in radius without being the most massive, and conversely, some of the heaviest stars are relatively compact. Mass sets the pace of stellar evolution. A star with high mass experiences immense gravitational pressure in its core, raising temperature and density. This accelerates nuclear fusion, producing enormous energy output and luminosity. However, mass does not directly determine radius. Stars of similar mass can have widely varying radii depending on age, evolutionary stage, and internal structure. Radiation pressure plays a key role in limiting mass. As massive stars form, the energy released from nuclear reactions and gravitational contraction generates photons that exert outward pressure. This pressure counteracts gravity. If the luminosity becomes too high relative to mass, radiation can blow away material, preventing further accretion. This self-regulating mechanism ensures that stars do not grow arbitrarily massive during formation. The principle governing this balance is known as the Eddington limit. It describes the maximum luminosity a star can achieve for a given mass before radiation pressure exceeds gravitational attraction at the surface. When a star approaches this limit, even small increases in energy output can drive mass loss. Stars near the Eddington limit are inherently unstable, with strong stellar winds ejecting material into surrounding space. Because of the Eddington limit, some of the most massive stars are not the largest in radius. For example, blue hypergiants and very massive O-type stars have extraordinary mass but comparatively smaller radii. Their high temperatures concentrate energy in a compact volume, producing tremendous luminosity without expanding outer layers as dramatically as cooler red supergiants do. Red supergiants and hypergiants, in contrast, achieve enormous radii during late evolutionary stages. Their cores have contracted, shell fusion occurs at multiple layers, and radiation pressure in the outer envelope allows expansion. These stars can extend over 1,000 times the Sun's radius, yet their mass may be modest relative to extreme O-type stars. Expansion is driven not by mass alone but by evolutionary physics and the balance of forces in the envelope. The interplay between mass and radius becomes especially clear when comparing different types of stars. A blue supergiant may have 10 or 20 times the mass of the Sun but only tens of solar radii. A red supergiant may have only a fraction of that mass but extend hundreds of solar radii. The contrast underscores that mass governs internal pressure and fusion rates, while radius is influenced by energy distribution, temperature, and atmospheric dynamics. Mass also affects stability and lifetime. Heavier stars burn fuel more quickly, exhausting hydrogen and advancing through evolutionary stages at a rapid pace. They may enter supergiant or hypergiant phases while still a few million years old. Lighter stars can remain on the main sequence for billions of years. The extremes of mass and radius reflect different aspects of the same physical processes: core temperature, fusion rate, and balance between gravity and radiation. Stellar winds connect mass and radius in practical terms. As stars approach the Eddington limit or enter late evolutionary stages, they lose material through strong winds. These winds can strip outer layers, reducing mass over time while maintaining or even increasing the radius temporarily. In red hypergiants, mass loss can shape the extended envelope and affect how we define surface, adding complexity to observational estimates. Rotation also plays a subtle role. Rapidly spinning massive stars experience centrifugal forces that reduce effective gravity at the equator. This can slightly inflate the star's outer layers, creating oblate shapes. Rotation interacts with radiation pressure and mass loss, further differentiating stars of similar mass in terms of radius. Observationally, determining mass is challenging. Unlike radius, which can be inferred from luminosity and temperature, mass is often estimated indirectly. In binary systems, orbital motion reveals mass through gravitational effects. For isolated stars, models based on spectroscopy, luminosity, and theoretical understanding provide estimates. These methods carry uncertainties but allow comparison among the most massive stars known. Understanding the difference between mass and radius helps clarify why stars like UY Scuti, Stephenson 2-18, and VY Canis Majoris hold records for size, while stars like our 136A1 or the Pistol star hold records for mass. Radius champions are often in late, expanded phases with diffuse envelopes, while mass champions are hot, luminous, and compact. Both extremes demonstrate the diverse ways stellar physics manifests in observable properties. You notice that the physics of mass and radius are intimately connected yet distinct. Mass controls internal fusion, pressure, and lifetime. Radius reflects outer envelope dynamics, temperature, and evolutionary stage. Radiation pressure and the Eddington limit act as regulators, ensuring that neither mass nor size can grow without constraint. The result is a rich landscape of stellar diversity, where the largest and the heaviest stars occupy different regions of possibility. Through careful measurement and modeling, astronomers can separate these properties and understand their implications. Observing variability, accounting for mass loss, and considering evolutionary stage all contribute to a clear picture of how stars exist at the extremes. Recognizing that size and mass are not synonymous allows you to appreciate why one star can be a radius champion while another dominates in mass. As you reflect on these distinctions, you sense the subtle balance of forces shaping the stars. Gravity, radiation pressure, fusion, and mass loss interact continuously, defining structure and stability. This understanding prepares you to examine the most massive stars known, whose extraordinary energy output further illustrates how mass shapes the cosmos in ways distinct from sheer size. R136A1 is among the most massive stars identified to date, residing in the dense star cluster R136 within the Tarantula Nebula of the Large Magellanic Cloud. Unlike red supergiants, it is a hot, luminous blue star. Its immense mass makes it an ideal case study for understanding the upper extremes of stellar formation and evolution. Unlike size records, which often involve expanded red supergiants, mass records emphasize the amount of matter contained in the star's core and envelope. Mass determination in stars like R136A1 relies on indirect but precise methods. In close binaries, astronomers can observe orbital motion and apply Newtonian dynamics to measure mass. For isolated stars, such as R136A1, mass must be inferred through stellar modeling. Spectroscopic data reveal surface temperature, luminosity, and composition. These values, combined with theoretical models of stellar structure and evolution, allow astronomers to estimate mass within reasonable uncertainties. Spectroscopy is crucial for this process. Light from the star is spread into a spectrum, revealing absorption and emission lines that indicate the elements present and their ionization states. Ionization depends on temperature and pressure, which correlate with mass. By comparing observed spectra with theoretical models, astronomers can constrain the star's properties, including its mass and age. High-resolution spectra provide finer constraints, reducing the range of possible masses. The mass of R136A1 is extraordinary. Estimates place it around 200 to 250 times the mass of the Sun, though uncertainties remain due to limitations in modeling and observational constraints. Such a massive star generates enormous luminosity, over several million times that of the Sun. This output drives intense radiation pressure and powerful stellar winds that carry mass away from the star at significant rates, reshaping the envelope over time. Massive stars lose material continuously through these stellar winds. Radiation pressure accelerates gas and plasma outward, forming high-speed flows that can reach thousands of kilometers per second. The mass loss rate is substantial. Over millions of years, a star like R136A1 may shed tens of solar masses. This process affects both the star's evolution and the surrounding interstellar environment, enriching nearby regions with heavy elements formed in nuclear fusion. Unlike radius records, where expansion is temporary and occurs late in a star's life, mass records depend on the initial formation and early evolution. A star can be extraordinarily massive without having an extremely large radius. The energy from fusion in a compact, hot star produces outward radiation that counteracts gravity, but does not require the outer layers to expand dramatically. Hot, blue massive stars therefore appear smaller in radius than evolved red supergiants, despite containing more mass. Understanding the upper limits of mass involves considerations of star formation physics. Gas clouds must collapse against thermal pressure, turbulence, and magnetic fields. Radiation emitted by the forming protostar creates outward pressure that can limit further accretion. The most massive stars form only in dense clusters where local conditions allow sufficient accumulation of material before feedback halts growth. This explains why stars like our 136A1 are found in active star-forming regions. Massive stars evolve quickly. Their high core temperatures accelerate fusion, and they progress through hydrogen, helium, and heavier element burning at an accelerated pace. While a star like the Sun may remain on the main sequence for 10 billion years, our 136A1 will exhaust its fuel in a few million years. Its brief lifetime is a direct consequence of both extreme mass and the corresponding high luminosity. Energy output shapes the structure and stability of these stars. The extreme luminosity produces radiation pressure that balances gravitational contraction, establishing hydrostatic equilibrium. In the most massive stars, this balance is delicate. Small changes in internal fusion rates or surface opacity can affect mass loss rates and drive variability. Despite this, the fundamental principles of stellar structure, core fusion, pressure support, and energy transport remain consistent. Observational challenges are significant. Our 136A1 lies in a dense cluster with other luminous stars, requiring careful separation of light sources. Its distance, over 160,000 light-years away in the Large Magellanic Cloud, adds further uncertainty. Measurements must account for interstellar absorption, cluster motion, and blending with nearby stars. High-resolution telescopes and adaptive optics are essential for isolating the star's properties. Comparing mass and radius records highlights the distinction between the two. Red supergiants may claim extraordinary radii, extending over 1,000 solar radii, but have relatively modest mass. Blue hypergiants and extreme O-type stars like our 136A1 carry enormous mass yet maintain smaller radii. The physics underlying these extremes differs. In one case, envelope expansion dominates. In the other, concentrated core pressure and fusion dictate properties. Understanding these massive stars also informs broader astrophysical processes. Their short lives, intense luminosity, and powerful winds influence star formation in nearby regions, trigger shock waves, and enrich interstellar material with heavy elements. When they eventually explode as supernovae, they seed the galaxy with the products of nuclear fusion, shaping subsequent generations of stars and planets. You notice that while our 136A1 and similar stars are extreme in mass, their sheer size is not what captures this distinction. Instead, it is the combination of concentrated energy output, rapid evolution, and feedback processes that defines their place in the cosmic landscape. Their existence emphasizes that the universe contains separate records for mass, radius, and luminosity, each governed by interconnected but distinct physical processes. By examining these most massive stars, you gain perspective on the diversity of stellar extremes. Mass champions demonstrate the upper bounds of formation and evolution, while radius champions illustrate the expansive outcomes of late-stage stellar physics. Observing both categories enriches your understanding of how energy, gravity, and matter interact to produce the extraordinary variety of stars in the cosmos. As you reflect on our 136A1 and its peers, you sense how energy output shapes structure, stability, and evolution. These stars illuminate the principles of physics at the extreme, reminding you that the cosmos is both predictable and astonishing in its range, offering a quiet lesson in the limits and possibilities of stellar existence. Every star exists in a balance between inward gravity and outward pressure. Gravity pulls matter toward the core, while pressure from nuclear fusion and radiation pushes outward. This balance, known as hydrostatic equilibrium, defines the structure of a star at all stages of its life. If gravity overwhelms pressure, the star contracts. If pressure exceeds gravity, the outer layers expand or may be lost entirely. This interplay establishes natural limits to how massive or large a star can become. Radiation pressure is particularly important in massive stars. As the core fuses heavier elements, photons exert an outward force on the surrounding plasma. When luminosity increases, this pressure grows. The Eddington limit provides a theoretical threshold. If radiation pressure at the surface exceeds gravity, the star becomes unstable, driving material outward in powerful stellar winds. In practice, stars cannot indefinitely exceed this limit without losing mass. For stars with enormous radii, expansion is often a temporary phenomenon. Red supergiants and hypergiants swell as hydrogen is exhausted in the core and shell fusion progresses. Their outer envelopes respond to reduced gravitational binding and elevated radiation pressure. Yet these expanded layers are tenuous and unstable, vulnerable to pulsation, convection, and mass loss. These processes act as natural regulators, preventing indefinite growth in size. Pulsations occur because the outer layers do not respond instantaneously to changes in core output. Small imbalances in pressure or temperature cause the envelope to expand and contract rhythmically. These oscillations can alter brightness, surface temperature, and apparent radius. Over time, repeated pulsations eject material, forming circumstellar envelopes or shells. Such mass loss reduces overall mass while the star temporarily maintains an enormous radius, illustrating the transient nature of extreme expansion. Mass loss is a crucial factor limiting maximum size. Stellar winds, driven by radiation pressure, expel gas from the outer layers at high velocities. In the most massive or luminous stars, this can amount to several solar masses over a million-year period. The ejection of material decreases gravity at the surface, further affecting structure. Yet it simultaneously reduces the fuel available to maintain hydrostatic equilibrium, gradually shrinking or destabilizing the star. In theory, there are upper limits to both mass and radius, though they are defined differently. Mass is constrained by formation physics and radiation pressure during accretion. Only in dense clusters can gas accumulate rapidly enough to form stars exceeding a few hundred solar masses. Radii are constrained by the star's evolutionary stage and internal physics. A star may temporarily swell, but extended, diffuse envelopes cannot remain stable indefinitely. Observed extremes therefore reflect both physical possibilities and transient states. Temperature also constrains size. Hot, massive stars concentrate energy in a compact volume, producing tremendous luminosity without extensive expansion. Cooler stars may expand to thousands of solar radii, but only after core evolution reduces binding forces. Energy transport within the star, via radiation or convection, determines how efficiently heat reaches the surface, influencing radius. There is no scenario in which a star can remain both extremely massive and indefinitely extended without violating physical laws. Rotation and magnetic fields add subtle constraints. Rapidly spinning stars experience centrifugal forces that reduce effective gravity at the equator, encouraging slight expansion, but also promoting instabilities and enhanced mass loss. Magnetic fields can channel stellar winds and influence envelope dynamics. These factors further limit how large a star can grow while maintaining structural integrity. Observational evidence supports these theoretical limits. Even the largest stars documented, such as UY Scuti, Stephenson 2-18, or VY Canis Majoris, show signs of pulsation, mass loss, or instability. Their radii fluctuate over time, and their outer layers are often diffuse and variable. No stable star exists with both extreme mass and extreme radius simultaneously. Instead, nature imposes boundaries that keep stars within a physically consistent range. Theoretical modeling reinforces this understanding. Stellar evolution codes simulate energy transport, fusion, and envelope dynamics. These models show that beyond certain mass or luminosity thresholds, stars either shed mass rapidly, explode as supernovae, or fail to form in the first place. Size, luminosity, and mass are therefore interdependent, constrained by fundamental forces and processes. Even with these constraints, stars continue to challenge observers. Revised distance measurements, improved spectroscopy, and infrared observations sometimes adjust estimated radii or masses, altering rankings among largest or heaviest stars. Yet every adjustment confirms the role of physical limits. Stars cannot grow without bound, and extreme properties are always moderated by the forces acting within and around them. You begin to see that the largest stars are temporary monuments to stellar evolution. Their immense envelopes reflect late-stage processes, radiation pressure, and weak surface gravity, but they are inherently unstable. Massive cores and high luminosity accelerate evolution, while pulsation and winds limit the persistence of extreme radii. In this balance, the universe defines natural ceilings for growth, while still allowing stars to achieve remarkable scales. As you consider these boundaries, you perceive a pattern. Hydrostatic equilibrium, radiation pressure, and mass loss combine to produce a universe where stars can be enormous, luminous, and brief in cosmic terms, yet never limitless. These physical principles quietly regulate stellar extremes, ensuring that even the most extraordinary stars follow predictable, measurable rules. Observing the largest stars in our galaxy is far from straightforward. Light from these distant objects must traverse thousands of light-years of space, encountering interstellar dust and gas along the way. Dust grains absorb and scatter visible light, dimming the apparent brightness of stars and altering the observed color. Without accounting for this extinction, estimates of luminosity, temperature, and radius would be systematically incorrect. Even a seemingly small amount of dust can create significant errors when multiplied across vast distances. Infrared observations are one way astronomers circumvent this challenge. Longer wavelength infrared light passes through dust more efficiently than visible light, revealing stars hidden behind dense clouds. Telescopes equipped for infrared measurements can detect energy emitted from the photosphere and surrounding layers of red supergiants and hypergiants. This allows more accurate determination of luminosity, which is crucial for calculating stellar radius using the Stefan-Boltzmann relation. Distance is another critical factor. The further a star lies from Earth, the more its apparent brightness diminishes, and small errors in distance lead to large uncertainties in inferred properties. Gaia, the European Space Agency's astrometric mission, has transformed our ability to measure stellar distances. By precisely tracking stellar positions over time, Gaia provides parallax measurements even for stars thousands of light-years away. These measurements improve estimates of luminosity and, in turn, allow for better radius calculations. For stars embedded in clusters or crowded regions, isolating the light from a single star presents additional challenges. Nearby luminous stars can blend their light, contaminating spectral and photometric observations. Astronomers must carefully decompose these signals using high-resolution spectroscopy, adaptive optics, and sophisticated image processing techniques. Without these corrections, size estimates could be significantly skewed, particularly for stars in dense star-forming regions like the Tarantula Nebula. Stellar variability introduces further complexity. Red supergiants and hypergiants often exhibit pulsations, with brightness and temperature fluctuating over periods of months or years. These changes affect observed luminosity and spectral characteristics. Accurate measurements require repeated observations over time, averaging out transient effects. Observatories often track these stars over decades to capture reliable data for radius and temperature calculations. Interstellar reddening also affects interpretation of spectral data. Dust preferentially scatters shorter wavelengths, making stars appear cooler than they actually are. Astronomers must apply reddening corrections based on models of the interstellar medium along the line of sight. Inaccurate corrections can produce significant overestimates or underestimates of radius. Infrared and multi-wavelength observations help validate these corrections by providing complementary data across the spectrum. Observing extremely distant stars compounds these difficulties. Some of the largest candidates lie tens of thousands of light-years away, within heavily obscured regions of the Milky Way. At such distances, even minor uncertainties in extinction or cluster membership propagate into large errors in radius calculations. High-precision photometry, spectroscopy, and distance measurements must be combined to reduce uncertainty and create a coherent picture of these extreme stars. Modern astronomical instrumentation has greatly enhanced measurement precision. Interferometers can resolve angular diameters for nearby supergiants, providing direct estimates of physical size. Space-based telescopes avoid atmospheric distortion, allowing stable observations in visible and infrared wavelengths. By integrating these tools with theoretical models, astronomers derive radius estimates that are increasingly robust, even for stars on the far side of the galaxy. Despite technological advances, uncertainties remain unavoidable. Measurement errors, variable stellar atmospheres, and dust obscuration all contribute to margins of error. Astronomers report these uncertainties alongside estimated radii and luminosities, reflecting the careful, conservative approach that defines observational astrophysics. This transparency allows comparisons between stars and helps refine models as new data becomes available. You also recognize the iterative nature of these measurements. Distance estimates improve, dust models are refined, and repeated spectroscopic observations update temperature and luminosity values. Each refinement contributes to a more accurate understanding of the largest stars, while simultaneously highlighting the limits of current observational capabilities. Even the most luminous and expansive stars challenge the precision of modern astronomy. The study of extreme stars therefore combines observational ingenuity, careful modeling, and patient verification. Astronomers must correct for every factor that can alter perceived brightness or spectral characteristics, from interstellar dust to crowding, reddening, and pulsation. Only by integrating these corrections can estimates of radius and luminosity approach reliability. As you reflect on these efforts, you appreciate the precision required to observe and measure the largest stars. Every photon reaching a telescope carries information that must be carefully interpreted, and every correction enhances understanding. The universe is vast and obscured in places, yet with meticulous observation, it reveals the properties of stars that stretch across unimaginable distances, allowing you to perceive scale, structure, and energy in ways previously impossible. Behemoth is not an official name recognized by the International Astronomical Union or any professional astronomical catalog. It has appeared in media articles and informal discussions to describe a particularly large or impressive star, but in scientific literature, the star is identified by its catalog designation, such as UY Scuti or Stephenson 2-18. Astronomers rely on formal identifiers that provide precise coordinates, cluster membership, and survey references, ensuring clarity across observations and studies. Stars receive their catalog names through systematic surveys. UY Scuti, for example, is named according to the variable star naming convention, where the first designation combines a sequential letter with the constellation name. Stephenson 2-18 is identified within a specific cluster survey conducted by astronomer C.B. Stephenson. These names provide unambiguous reference points, allowing astronomers worldwide to locate, measure, and compare stars consistently. The use of descriptive nicknames like Behemoth can be misleading. Media coverage often favors striking terms that capture public imagination, emphasizing extremes such as size or brightness. While these names may help readers engage with science, they do not reflect the rigor of observational data. Official scientific communication relies on catalog designations to avoid ambiguity, ensuring that research findings are reproducible and traceable. Peer-reviewed literature evaluates extreme star claims carefully. When a star is described as exceptionally large, researchers provide observational evidence, methodology, and uncertainty estimates. Measurements of luminosity, radius, and distance are documented, often across multiple studies. These publications undergo review to confirm that claims are consistent with established physics and observational protocols, ensuring that any assertion about a record-holding star is scientifically grounded. Informal names can persist in public discussion, even when precise measurements are available. For instance, UY Scuti is sometimes called a giant or colossal star in popular articles. These descriptors emphasize size, but they do not constitute formal recognition. In professional contexts, the star is always referenced by its catalog name, along with measured parameters such as radius, mass, and luminosity, and the associated uncertainties. Cataloging is essential because it provides standardized metadata. Each star entry includes right ascension and declination coordinates, apparent magnitude, spectral type, and survey references. These details allow astronomers to identify stars accurately, compare measurements over time, and update records as new data becomes available. Informal nicknames lack this precision and can lead to confusion if used in scientific reporting. The evaluation of a star's size or mass involves rigorous methods. Observers consider distance, luminosity, spectral classification, and variability. They apply corrections for interstellar extinction and analyze extended atmospheres to define a meaningful radius. When reporting an extreme star, Researchers provide all methodological details, so other astronomers can replicate calculations or verify estimates independently. Nicknames like Behemoth do not convey this level of detail. In some cases, descriptive names become associated with specific stars in outreach or educational materials. These names can be helpful for visualization or storytelling, but it is important to distinguish them from formal designations. UY Scuti remains the scientific identifier for the star, often called a behemoth in popular accounts, while Stephenson 2 to 18 and VY Canis Majoris have their respective catalog-based references. Misinterpretation can arise when informal terms are reported as scientific facts. Headlines may imply a newly discovered record holder or an unprecedented size without clarifying uncertainties or measurement methods. Researchers mitigate this by publishing precise measurements with error margins and emphasizing that size comparisons depend on methodology, distance estimates, and observational techniques. Official catalogs provide stability and clarity that media shorthand cannot match. Understanding the distinction between formal designations and popular nicknames reinforces the importance of rigor in astronomy. Scientific names, coordinate-based catalogs, and carefully documented measurements allow astronomers to communicate reliably about extreme stars. Informal terms, while evocative, do not substitute for verified data. Recognizing this distinction helps maintain accuracy when discussing record-holding stars or their extraordinary properties. You realize that while terms like behemoth may capture attention, astronomers focus on measurable quantities. Catalog names, luminosities, radii, and masses provide consistent reference points, allowing scientific progress and comparison. By relying on verified measurements rather than evocative labels, researchers ensure that records of stellar extremes are precise, reproducible, and rooted in observable reality, giving clarity to the study of the universe's largest stars. When you look across the galaxy and beyond, a handful of stars consistently emerge as candidates for the largest in terms of radius. UY Scuti, Stephenson 2 to 18, and VY Canis Majoris dominate these lists, each presenting unique observational challenges and uncertainties. Their apparent enormity is a result of careful measurements of luminosity, surface temperature, and distance, combined with corrections for interstellar dust and atmospheric extension. None of these stars can be observed with a solid, sharply defined surface, making precise measurement a nuanced task. UY Scuti, located in the constellation Scutum, is often cited as a radius record holder. Its distance of roughly 9,500 light-years has been refined through parallax and cluster analysis, while infrared observations help mitigate obscuration by dust. The star's effective temperature, measured at approximately 3,365 kelvins, together with its luminosity, allows astronomers to calculate a radius of roughly 1,700 times that of the Sun. These values carry uncertainties, but they provide the most reliable estimate given current observational capabilities. Stephenson 2 to 18, part of a dense star cluster, illustrates the challenges of distance and crowding. Its radius estimates, which range from roughly 2,000 to 2,150 solar radii, depend heavily on accurate distance determinations to the cluster. Spectroscopic analysis reveals a relatively cool outer layer, typical of red supergiants, while infrared data minimizes interference from interstellar dust. The extended, diffuse nature of its atmosphere necessitates careful definition of the photospheric boundary, further contributing to uncertainty. VY Canis Majoris, once believed to be the largest known star, exemplifies the importance of continual revision. Earlier estimates placed its radius well above 2,000 solar radii, but improved distance measurements, spectroscopic temperature analysis, and modeling of its extended atmosphere reduced that figure. The star remains among the largest observed, with an inflated envelope shaped by mass loss and pulsation. Its example demonstrates that apparent records can shift as methodologies advance. Each of these stars highlights the distinction between physical size and other stellar properties. Large radius does not necessarily correlate with mass. Many red supergiants are relatively modest in mass compared with blue hypergiants or extremely massive O-type stars. Observing these extremes requires understanding both the internal structure of the star and the behavior of the tenuous outer layers, which can expand dramatically while containing relatively little mass. Observational refinements continue to adjust rankings among these candidates. Improved parallax data, infrared imaging, and high-resolution spectroscopy allow astronomers to reduce uncertainties in luminosity and radius estimates. Variability in brightness and pulsation is monitored over years, averaging out temporary fluctuations to produce more stable measurements. Even slight changes in distance or temperature measurement propagate into large changes in inferred radius, emphasizing the dynamic and provisional nature of these records. Measurement of extended atmospheres also relies on defining a consistent reference point. The photosphere, or the layer from which most visible light escapes, is not sharply defined in red supergiants. Astronomers choose an optical depth where the star becomes effectively transparent to light, acknowledging that outer layers continue beyond this point. These methodological choices are documented carefully in the literature, enabling comparison across different studies and stars. Beyond individual measurement techniques, comparing these largest stars highlights broader astrophysical principles. Radiation pressure, hydrostatic equilibrium, and stellar evolution dictate the limits of expansion. Red supergiants achieve their extraordinary radii late in life, after core hydrogen has been exhausted and shell fusion drives envelope inflation. Pulsation and mass loss ensure that no star can maintain these extreme radii indefinitely, regulating both size and stability. You recognize that no single star permanently holds the title of largest. As observations improve, distance estimates are refined, and atmospheric models evolve, stars can move up or down in rankings. This fluidity is not a flaw but a reflection of the scientific process. Evidence accumulates, methods improve, and understanding becomes more precise over time. Even in the extremes of the universe, science remains self-correcting and iterative. In reviewing the largest stars, a pattern emerges. Size extremes correspond to late evolutionary stages, relatively low surface gravity, and tenuous, pulsating outer layers. Observational data must be carefully interpreted, accounting for dust, distance, and variability. Cross-referencing multiple studies and instruments ensures reliability, emphasizing that understanding these giants requires both patience and precision. Ultimately, these stars reveal the vastness of the cosmos while remaining accessible to measurement. Their enormous radii, though difficult to observe directly, are grounded in physical laws and quantifiable data. The process of measuring, correcting, and refining estimates illustrates the careful, methodical approach of astrophysics, showing that even in regions of extreme scale, the universe can be studied with clarity. As you consider UY Scuti, Stevenson 2-18, and VY Canis Majoris, you feel a quiet awareness of the boundaries of observation. Science does not provide permanent titles or absolutes, but it does offer evidence-based understanding that grows more precise with each measurement. These largest stars, extraordinary yet measurable, remind you that the cosmos, in all its extremes, remains within the reach of careful inquiry, offering both wonder and comprehension.